All right, so as you know, yesterday we finished up Unit 1 for Algebra 2. Okay, I asked you to take those 3 quizzes and your unit test, right? So again, most of your unit tests should be unlocked, but if you come across a unit test that is not, please let me know, and I'll get that as soon as possible, okay? So again, most of you should have your tests unlocked, but if not, let me know and I'll get that as soon as I physically can. All right. So if we look at our schedule here today, again, we got to cover another 3 units so we can keep up this this pace that we have set here. All right. So today we are going to move on to Unit 2. Okay, we're going to move on to Unit 2, which is radical expressions and functions. Okay, radical expressions and functions. And my goal is, again, of course, by the end of today, we're going to cover from 2.1 to 2.3. Okay, that's my goal, is to cover all the way to 2.3. All right, so let's get rolling here. If we look at the overview for Unit 2 here, radical expressions and functions. Let's take a look here.
Have you ever heard the phrase, compare apples to apples? You might have had to use it in an algebra class if you've ever had to collect like terms. Some things combine together easily. Some things don't. And some things might seem hard to combine until you transform them. That's the story of radicals and rational exponents. Radicals are just another type of exponent. You can treat radicals like any other exponent and use them to answer questions about the world you live in. How is the volume of music related to how far I am from the speaker? How does the acidity of my stomach depend on what I had for lunch? What is the relationship between the radius of a bubble and the space it takes up? Radical expressions and functions are useful tools for creating many more mathematical models like these.
Okay, so again, just a quick overview there. Again, we're going to focus a lot on radical expressions and functions, and hopefully you picked up that little key there. Radicals are just a different form of exponents, right? They're just a different form of exponents. But we'll start off here with the basics of radicals. Okay, so again, if you're confused what we're talking about with radicals, we're talking about this square root function, right? Or this root function in general. Okay, this root function in general. All right, so we'll define what that means, and then we'll look at this in this first unit, starting with the basics of radicals here. All right. Okay. So starting off here, talking about speed limits, right? Talking about speed limits, and we introduced this. I can't remember if it was today or yesterday or the day before. But remember, when it says miles per hour or something per something, right? This is making it into a fraction. So you've got 10 miles per hour. That would be 10 miles over 1 hour, right? That would be 10 miles over 1 hour. All right. But we're asking, of course, where does a radical expression come into play in this scenario of if for every 10 miles per hour you drive, you should leave 1 car length between you and the car in front of you. Okay. So looking first here, what they define as a radical expression, right? That is an expression that contains 1 or more of the radical signs, right? And the radical sign is, of course, this sign that we take the root of, right? So if we look at this car problem, right? We look at it together.
Police officer arrives at the scene of an accident where one car has clearly hit the back of another car. The car that caused the damage left skid marks on the asphalt road before hitting the car in front of it. These skid marks measure 97 feet in length. By looking at the amount of damage to the two cars, the officer is able to calculate that the car was going 35 miles per hour when it hit the other car. But the officer must now figure out if the driver of the back car was going more than the speed limit of 50 miles per hour before starting to skid. In other words, did this driver break the law?
Okay, so again, if we're using this principle that you've got to keep 10 feet in front of you, right, and they realized how long the skid marks were, how fast they were going when they hit the car, right, there's all these different factors here. So this officer is obviously trying to figure out, was he going more than the speed limit of 50 miles per hour before it started to skid, right? Was he speeding? All right, so then if we look here, besides the speed of the car when the driver hit the brakes, what other factors might affect the distance that the car will skid, right? And the answer is going to be all of the above, right? All of the above. Hopefully, for those of you who are learning to drive or are already drivers, you should know that weather is a big factor, right? It's not anything to be afraid of. It's just something you have to take into consideration when you're driving, right? The slope of the road, is it sloping downwards? Am I more prone to going down a hill or up a hill, right? And then obviously the road surface. Okay, something that's paved like asphalt will be a little bit easier to drive on maybe than something that's unpaved like a dirt road, right? So all of those above could potentially have an effect here. All right, this is going to be important because obviously, you know, at the end we're going to have to solve this problem here. Okay, so moving forward here, radicals in math. Okay, the word radical is used to denote our root function. Okay, and usually if we just show it like this, it indicates a square root. All right, and for terminology here, the value that is under the radical sign is called the radicand, right? It's called the radicand. So if I had square root of x, right? If I had square root of x, then the x would be the radicand. Okay, the x would be the radicand. All right, so for example, perfect. If I've got 4 squared equals 16, if I've got 4 squared equals 16, and negative 4 equals 16, okay? If I were to take the square root of 16, obviously we know that the roots would be positive and negative 4, okay? Positive and negative 4, all right? And we can say also this thing called the principal square root, right? So the principal square root, that's the number that, or the value that's going to come out of taking the square of something, right? So whether it's positive or negative, right, one of our principal square roots is going to be 4. All right, looking at now, if we have 81, right, the square root of 81. So if we have the square root of 81, we know it's going to be plus or minus, okay, plus or minus 9. But the value of 9 is our principal square root. Okay, our principal square root. Okay, so again, looking at inverse operations, right? The inverse operation is the operation that's going to undo the function of another, right? So that's the whole point is we've got to be able to go forwards and backwards with these mathematical operations here. Okay, so sorry. So a radical is the inverse operation of an exponent, right? A radical is an inverse operation of an exponent. So if we take a look back here, right? 4 squared, right? So squaring, that's my exponent here. But if I want to undo 4 squared, right? That's taking the square root. So that's the inverse operation here. It's taking the opposite and getting back to my original. So again, looking here, if I have n root of a, right? That's how you'd read this. This is the nth root of a. Okay, its inverse operation is a to the power of n. It's a to the power of n. And if we take a look here at just more specifics, okay, we define this that a now, the thing under the square root symbol or under the root symbol is called the radicand, right? It's the radicand. Okay, and radical symbol, And then again, this is our nth root, right? It's the nth root. So again, it could also be called the index of the radical. Maybe you've heard it called the index, all right? But it's going to be the same exponent. So for example, if you look at that bottom one, if I have the third root of a, and that's, again, sorry, I can't move it, but where it says 3 root a, okay, that's saying the third root of a, okay, the third root of a. If I want to undo that or look at the inverse operation, I'm looking at y cubed equals a, right? I'm looking at y cubed equals a, all right? So it would be the same value there. Again, obviously with the index and the a value, we need to make sure that they're consistent. That's how we would be able to undo those different functions here, okay? And obviously if that value is not written, so if there's no value here for n, we are assuming it's the square root, right? So we only start writing a number here for n if it's 3 or above. Okay, and then if we have a to the power of n, right, a to the power of n, a is our base number, okay, a is our base number, and then n is our exponent, okay, n is our exponent. All right. Perfect. So we'll keep going there, and hopefully you saw that it said mostly we're going to focus on square roots in this unit here. All right. But again, we use this a lot when we're looking at the perfect squares, right? Trying to figure out what can get added together to do this thing called perfect square, right? So we dealt a lot with that, and looking for some basics that we know for square, right? So square root of 49, obviously 7, okay, 4, 12, 25, all right? Sorry. But we can also deal with things that aren't perfect squares, right? So we can deal with things that aren't perfect squares or don't perfectly reduce down, okay? And we'll talk a little bit more, we'll talk a little bit more about that. So, but a couple examples here would be like if I have the square root of 12, right? Can I reduce that down to anything to make it a little bit smaller, a little bit nicer? And the answer is going to be yes on that one. Okay, it's going to be yes. And obviously we know that there's a lot of practical applications, okay? Especially some that my juniors have been working a lot with, right? The Pythagorean theorem. Okay, if I have to figure out the sides of a triangle, okay, sometimes you might have to take the square root of something, okay, and it might not always give you a nice area. Or sorry, a nice answer. All right, a couple other ones is if you have to take areas of things, right, maybe circles, areas of squares, anything where you have something raised to an exponent, you have the potential of having an answer be in radicals, right? So again, for example, if we're solving any of these, we might have to take the square root of our answer to get these values by themselves. So for example here, a squared plus b squared equals c squared, right? Well, to get c by itself, I have to take the square root of both sides, okay? And since I have c squared and square root, then that cancels themselves out. Same thing here, if I've got a equals s squared, if I take the square root of both sides, it cancels out that exponent. Okay, it cancels out that exponent, but I am left with the square root of a. All right, and then finally the same thing here, a equals pi r squared. All right, this is very similar except for we had to do one extra step. We had to move pi to the other side before we took the square root of both sides. But again, if I have a square root and I have something squared, those guys cancel each other out. So when I took the square root of s, the square root symbol and the and the exponent cancel each other out. All right. So again, for these values, if you have either side, right, you can solve the answer. So it says if a square has an area of 64 centimeters, what's the length of one side? All right, we could solve that problem. Okay, and we would look at for this one, it would be 8 centimeters. Okay, but what we would do is we would plug in 64 centimeters squared here for A. All right, we would plug in 64 centimeters squared here for A, and that would equal our S squared. All right, that would equal our S squared. We take the square roots of both sides, and then obviously the square root of 64 gives us 8. All right, And finally here, I'll highlight it. You have to note that when we're dealing with real world problems or things that have units attached to them, right? You also have to do the operations to those units. Okay, you have to do those operations to those units. So notice here, we started off with 64 centimeters squared, or cm squared. All right, so when we took the square root of 64, we also took the square root of centimeters, right? Or centimeters squared. So we are left with, again, square root of 64 gives us 8, and centimeters squared. The square root of that just gives me centimeters. So I'm left with just 8 centimeters there. All right, so again, being careful with your units, because those could be a couple easy points that you might lose if you're not paying specific attention. All right, so then you could have an expression that contains one or more radicals, right? And this is called a radical expression, all right? So this is called our radical expression. And so then there's a couple important properties that we have to discuss, all right? And the first one we've talked about a lot, so I don't want to harp on it too long here, all right? But the first one here is that for any number A and non-negative number B, all right? Any number A and non-negative number B. All right, so again, for example, if I have the square root of, I know this is a little confusing here. All right, but basically what they're trying to say is that if I have the square root of a number, right? So this is supposed to say 16 here, right? So 16 can either give me a positive or negative 4, right? When I take the square root of it. So I'm going to get a positive and a negative value when I take a square root, because basically I could have 4 squared or negative 4 squared, and they would both give me the same answer there. All right, so for any, if I'm taking the square root of any non-negative number, okay, if I'm taking the square root of any non-negative number, all right, so square root of 49, this could be positive 7 or negative 7. All right, it could be positive 7 or negative 7. All right, so the square roots and squares, I believe the answer should be sometimes negative. What? Oh, inverse operations. Okay, all right, well, square roots and squares are sometimes negative, right? As we know that, but I guess in this answer, they're looking for their inverse operations, right? One can undo the other, okay? One can undo the other, all right? Even though, as you can see here, you can still have negatives. We'll talk more about that later on, all right? So for this one, we're looking for square roots and squares are inverse operations, all right? And then I introduced this earlier, okay, that principal square root. So again, that's the absolute value of whatever your answer is. So again, if I have the square root of 64, right? If I have the square root of 64, that can give me a positive or negative 8. But regardless, the absolute value is going to be 8. So 8 would be my principal square root. All right. So then here, there's a garden example. If we're building a square garden, we've got 45 square feet. All right, so we know that our area has to be 45 square feet. So the answer, or the question is then what is our side length? Okay. So then here, when we take our square root, we have square root of 45 that gives us about 6.7. Okay, and as you can notice here, it's got a positive and a negative side. Okay, positive and negative. So then again, this is where you have to think practically. Okay, well, we're trying to build a garden. I can't have negative area in a garden. Okay, so my answer obviously has to be positive 6.7 square feet. Okay, 6.7 square feet. All right, and then just a key trick here, if you had to estimate a square root without a calculator, all right, what you would do here is you would find values that you already know the exact square root of, right? So for example, what value when it's squared is close to 45? All right, and I immediately think, okay, 7, because 7 squared gives me 49. Okay, 7 squared gives me 49. right? So that's pretty close to 45 here. All right, that's pretty close to 45 here. So I know that I'm close to 7. I'm on the underside of 7. So I'm going to be close to 6, right? And you can do the same thing. Okay, well, what's 5 squared? All right, well, 5 squared is 25. So I'm way closer to 7 than I am 5. Okay, so I'm going to be 6 point something, right? Or what's the square root of 6? 36, right? So again, I'm between 6 and 7. All right, so then other properties of radicals, right? Other properties of radicals. All right, so what we can do here, if I have 2 radicals, right? If I have 2 radicals and I'm multiplying them together, what I can do is I can combine them and write them under the same radical. So if you notice here, if I've got square root of a times by square root of b, that is equal to the square root of a times b, right? I can just write them all condensed together, right? So for example, square root of 2 multiplied by square root of 8, that's just like saying the square root of 2 times 8. Square root of 3 times 7, square root of 5 times 6, right? And again, this is going to become really helpful because some of these combinations, okay, some of these combinations might be easier for us to take the square of than individually trying to take the square of 5 and taking the square of 6, right? So this is a nice property that might help, okay? However, this only applies to multiplication, not addition or subtraction, okay? So if I had square root of 2 minus the square root of 8, you can't just combine them and say 2 minus 8, right? So it has to be multiplication in order for this to work, all right? So again, here, what we can do is, in order to simplify a radical, we can factor out the perfect squares, we can split the radical into products, and then we can simplify. So for example here, if we factor out a square of 12, okay, we factor out a square of 12, that gives us the square root of 4 and the square root of 3, all right? So because 4 times 3 gives us 12. 4 times 3 gives us 12, all right? Now we take that relationship we just learned and we can now split them up. This is like saying the square root of 4 times the square root of 3. All right. And what we can do now is because the square root of 4 is something that we can easily simplify, right? It now becomes 2 times the square root of 3, or 2 square root of 3. All right, 2 square root of 3. Because again, the square root of 4 equals 2. All right. So again, this is how we can simplify things that aren't necessarily easy. So first off, we have 50. Okay, we're gonna factor out a square. All right, factor out a square. So you could have done 5 and 10, right? You could have done 5 and 10, but then we'd be in the same predicament. How do I simplify the square root of 5? You don't, right? So what we're doing is we're looking for something that can be easily factored. Okay, easily factored, and then we could take the square root of. All right, so for example, 25 and 2, okay, that still gives me my 50, but now when I split them up, I have the square root of 25 and the square root of 2. Well, I can easily do the square root of 25. That gives me 5, right? So I can then rewrite this as 5 square root of 2. So square root of 50 can get simplified down to 5 square root of 2. All right, last one here. I've got 45. Okay, so I need to factor out something that can be squared. All right, so I've got 9 and 5. All right, 9 times 5. I'll split those up. I've got square root of 9 and square root of 5. Well, square root of 9 is a perfect square, so I can take that. That's going to be 3. Right, and when I simplify, I'm going to get 3 square root of 5. I can get 3 square root of 5. All right, so again, these are a way to simplify values down that aren't immediately obvious here. All right. And sometimes there can be more than one way to simplify a radical expression. All right. And again, it's basic rules of math here. As long as you're following appropriate laws, you're not getting rid of any numbers, you're not doing anything, that's breaking a rule here. It's going to combine to the same end result here. So for example, if I combine this first, square root of 3 times by 15, that gives me 45. I factor out a square. That can be 9 times 5, right? That can be 9 times 5. I split it up, I simplify, I'm still going to get the 3 square root of 5. All right. Or if I factor out, immediately, I can split up, I can simplify further, 3 square root of 5. All right. And again, the reason they kind of skipped a step here, but basically if I were to combine square root of 3 and square root of 3, that would give me square root of 9, which we know again is 3. So there's multiple ways that you can approach this, and you should get to the same answer as long as you're using your principles and your processes correctly. Okay. So moving forward here, a radical expression is an expression that contains one or more, obviously, radicals, right? One or more radicals, okay? And then looking at the properties of those, right? Those were just our ability to combine radicals if they are being multiplied together, all right? So again, this one's talking again, principal square root. So yes, this could be positive or negative 12. When we're talking about principal square roots, we're talking about the positive value there. So that's going to be 12. All right. Then here again, I'll leave these for you guys, but we have square root of 7 times square root of 12. Okay, square root of 7 times square root of 12. All right, this doesn't easily simplify right off the bat. So what you're going to have to do is you're going to have to combine those. So you're going to have to take the square root of whatever 7 times 12 is, right, and simplify down the best that you can. So first you're going to have to combine, then you're going to have to factor out a perfect square, and then you're going to have to simplify from there. Okay, so again, I'll leave these for you guys to try here. All right. So same thing here. I've got 6 times 10. That gives me 60. So I've got my square root of 60. Then I have to factor out a perfect square. Okay, is there something in here? Is there something in here that I can factor out in order to simplify this product down? Okay, and the answer is obviously going to be yes. Okay, it's going to be yes. But first off here, I can point out there's going to be one answer that's immediately should be not in your head. All right, for answer B is immediately incorrect. Okay, answer B is immediately incorrect, so don't fall for it. Because again, remember, when I'm multiplying these together, all I'm doing is extending this radical sign over both of these. So again, I've got the radical of 6 times 10. So 6 and 10 both go under the same radical. All right. This is going to be the same thing here. Again, I can extend this entire thing. All right, I've got 2, 6, and 3, so I can combine these in whatever way, shape, or form. All right, so I'll have 2 times 6. Then that product's going to multiply by 3. And then if necessary or if able, I'll simplify down to just one value here. And if not, if I can't simplify to one value, then hopefully I can find the appropriate product here. All right. And then finally, again, same thing. Which of the expressions below are equal to the one in the box? Okay, so you're going to have to take some time here and actually go through these and figure out which of these are correct here. All right, take a moment to go through which of these are correct here. All right, but again, regardless, they should all equal the same thing here. And if 6 square root of 2 is the most simplified form, okay, you shouldn't have anything more simple than that, right? So what I mean by that is immediately, okay, immediately D and E are incorrect answers. D and E are immediately incorrect answers. And the reason that is because 6 square root of 2, okay, if that's the smallest version of this, if this is as small as we can get this, okay, you can't have something else that is also in its simplified form. These two don't equal each other, right? They don't equal each other. So we can't have those being correct answers there. All right, and then obviously, again, one more problem here, okay? Combine them, factor out something that could be simplified if possible, and then do your simplification from there. All right, and the same product here, or sorry, the same principle applies to quotients. Okay, same product applies to quotients. So if I'm trying to divide by 2 fractions, or sorry, divide by 2 radicals, okay, I can just combine them under the same thing. So if I have the square root of A over the square root of B, I can take the square root of A divided by B under one radical symbol. All right, so again, the process is combine, the radicands, divide, simplify. So combine, divide, and then simplify if necessary or possible. All right, this one, 12 divided by 3. Okay, I'm going to combine. We know we're going to get a 4 here. I can obviously simplify that down to 2. All right, 50 divided by 2, that's going to give us square root of 25, which we know is equal to 5. All right, so again, combining when possible, and then following through your mathematical processes and simplifying. All right. And then obviously, again, that this could help simplify the square root of a fraction if it's not easily simplified, right? So I can do the other processes. So if I have the square root of 11 over 4, right, I write these as 2 square roots, and we don't know what the square root of 11 is off the top of our head, okay, but we do know that the square root of 4 gives us 2, so I can write this as square root of 11 over 2. Same thing here. Square root of 49 over the square root of 81. Okay, well, that's clearly going to simplify to 7 over 9. All right, it's going to simplify to 7 over 9. Same thing here. I've got square root of 10 over 9. And I can simplify the denominator to just 3 there. Okay, so again, knowing that we can go forwards and backwards and understanding this property fully is going to be super helpful. Okay, so then if we combine them both together, all right, we combine them both together. I have the square root of a fraction multiplied by a square root of another fraction. Okay, so what I can do is I can first combine them. All right, and now we know, or we should remember, that when we multiply by 2 fractions, we're going to flip the second fraction. Or I'm sorry, I lied to you. That was when we were dividing. Ignore me. So let me go back there so I don't confuse you. All right, so we're just multiplying, not dividing. My apologies. All right, when we're multiplying, we're just going to combine, multiply straight across, right? So 1 times 4 and 3 times 3. So this should give me 4 over 9 here. All right, and then since this doesn't simplify easily, we can split this up, square root of 4 over the square root of 9, and then we can simplify to 2 over 3. Okay, we can simplify to 2/3. All right, so then to confirm what we know, to simplify the square root of a fraction, you can find the square root of a number and the square root of the denominator. Okay, you can find the square root of the top and the square root of the bottom, and then you can simplify from there if either of those can be simplified. All right, so again here, this one here, you might want to combine first before you simplify. So if I look at this immediately, I don't know what the square root of 45 is, but if I combine them and I do 45 divided by 5, this is going to give me a combined value of square root of 9. Okay, square root of 9. So then if I have the square root of 9, it's going to give me my answer of 3. It's going to give me my answer of 3. All right. And yes, technically, in my opinion, it also should have been able to be -3, right? Because -3 squared still gives us 9, and so does 3 squared, okay? But when we're dealing with this, if you have the option between the positive and the negative value, choose the positive value, all right? Same thing here. If I have 162 divided by 2, all right, off the top of your head, it turns to 81. So this one's already kind of done step 1, so this turns to 81. 81 squared is, or I'm sorry, the square root of 81 gives us 9. Okay, square root of 81 gives us 9. Now this one I'll leave for you guys. Again, you're going to combine these using that first principle we learned. So combine these two by multiplying them together under the same radical symbol, and then simplify if you can from there, or split it up into the numerator and denominator and simplify the options as you go. Okay, so same thing here, right? Combine, simplify if possible. All right, combine and simplify if possible. All right, and what you might need to do here is, obviously we have the square root of 4. So this one can be immediately simplified into 2. Okay, this one can immediately be simplified into 2, but you have to be careful because if this wasn't the square root of 12, let's say this was the square root of 24, okay? This answer right here could be simplified into the square root of 24 over 2, okay? Square root of 24 over 2. But it might have a smaller form. It might have a more simple form. So you have to be very, very careful with how you simplify these. Okay, you have to be careful with how you simplify these. Okay, same thing. Just be very careful to make sure that you're in the absolute lowest form here. Awesome, awesome. Okay, so then again, just being super, super careful and making sure that every step of the way, you're making sure you check to see if there's equivalent forms of the expression above. Okay, so there are going to be multiple forms that could be correct for that process. All right, so then taking a look at our study sheet here, okay, again, it's all about the radical and the radicand, right? And we know that this is the inverse function of taking the square, right? So it's the inverse function for squaring, or how to undo if I square a value, right? So then we're talking about the principal square root, okay? So the principal square root, meaning it's the absolute value of a. So if I have 4 squared here, right, that's 16. If I took the square root of 16, my principal value is going to be 4. All right, my principal value is going to be 4. All right, and then again, remembering that if I have the square root of something and it's squared, or if I take a squared value and I take the square root of it, right, those values are going to cancel each other out, or those operations will cancel each other out. So I'm just left with the radicand. All right, and then knowing that we have this product property of radicals where I can combine them under the radical. And then I have the same thing for the quotient property. Right, I have the same thing for the quotient property. And the steps here are pretty much the same, or can be manipulated in different ways, right, as we found out. So you're going to try to obviously then combine them under the new radical symbol. And again, you're just looking for ways to simplify, whether that's splitting them into 2 radicals, right, whether that's combining them under 1 radical, right, it's going to be whatever works best for the numbers that you're given. Right? It's whatever works best for the numbers that you are given, right? So going from there, okay? So then if we go and look at this, we have 2 quizzes here, all right? So simplifying the products of radicals, right? So doing that multiplication, and then we have simplifying the quotient. So yes, you do have to do both of these, okay? And for the sake of time, I'm not going to go too in depth into the checkup here. All right, just my word of advice here is paying attention to your operations, making sure you're not skipping any steps here, okay? And then getting it down into the simplest form possible. Getting it down into the simplest form possible. All right, so simplest form possible. All right, and then again, being careful with, they told you exactly how to simplify it. Get it down to this or that. Right, get it down to this or that. All right, same thing here of these division problems, okay? Getting it down to the simplest form of the radical there. All right, simplest form of the radical. Okay, so that's unit 2.1 here, and again, you have 2 quizzes for that guy. All right, so then looking here, multiplying and dividing those radicals. All right, so if we look at multiplying and dividing those radicals, okay, we can now, if we understand these principles here, we can now multiply and divide radicals that don't just contain numbers, right? So we understand now, hopefully, the principles, okay, and then how we can do that with numbers. So now we can look at that with radical expressions that contain variables, right? So again, if I have the square root of 2x and the square root of 2 times by x, right? So again, being careful that x doesn't look like it's under the radical symbol. All right, so you can't confuse these, right? You can't confuse these. That's the square root of 2x and then the square root of 2 times by x. All right. So then here, if a radical is multiplied by a number or a variable, you should put it out in front of the radical to make it very, very clear, right? Because again, these look very similar here. So what you should do to be careful is you should have, or they should have, right? But when you're doing this, you should write it like this first value here. So this should be x square root of 2. Okay, you should look at x square root of 2. So you can avoid issues like, is it under that line? Is it not under the line, right? This is just a good practice to get in the habit of. All right, so again, these are not the same thing, but to make it clearer, you should write it out in front there. Okay, so then again, we saw the product rule of properties, okay, and we saw how these variables undo each other. Okay, we saw how these variables can undo each other. So again, if I take the square root of something squared, okay, it's going to give me that principal value. Okay, it's going to give me that principal value out. It's the same thing with variables. All right, if I have x squared and I take the square root of it, I'm going to get an absolute value of x. This could have been negative x, this could have been positive x, right? But when we're talking about principal values, it's the absolute value of x. All right, and again, the same thing works for operations here. So when we were dealing with our factors, if I had an x plus 1 squared, I can take the square root of that, and it's going to give me the absolute value of x plus 1. It's going to give me the absolute value of x plus 1, right, of that entire thing, right? Because that operation of squaring is for this entire binomial, right? So when I take the square root, it's the square root of this factor that's being operated on this entire binomial. All right. And then again, same thing, they cancel each other out. Okay, they cancel each other out the other way. So if you see it here, if I've got something square, the square root of something, okay, if I've got the square root of something, in order to undo that function, I take the square of it. All right, and those cancel each other out. If I was given the square root of x plus 1, okay, the square root of x plus 1, in order to get rid of this radical, right, I would square it. All right, I would square it. All right, so then multiplying radicals, it's going to have the same fashion here. All right, you can put them both underneath that radical symbol here. All right, and you just have to make sure that you're doing like terms, right? Looking at like terms. So when I'm combining 5x times by 20x, all right, they're both under radical symbols, so I can combine them. So it's like saying 5x times by 20x, right? And we know that we'd have to look at combining both of those. So 5 times 20 gives me 100, and x times x gives me now x squared. All right, it gives me x squared. And I can simplify this further into 10x, right? Into 10x. And if you think about it here, you can do this in multiple ways. Well, you can know that 100 is a perfect square and x is a perfect square. Okay, so that's going to simplify. Or you can do the inverse of what we just did here. We could take square root of 100 times by the square root of x squared. And that still simplifies down to 10x here. All right, for this one, I've got 2x times by the square root of x. So I'm going to combine those. That's going to give me 2x squared here. All right, and this is what we're talking about. We're going to factor out the square. So this is like saying x squared times by 2, right? Once I've combined them, it's like saying x squared times by 2. I can write them as 2 separate radicals, and then I can simplify the one that is simplifiable. Right, so my x squared, I can get that down to x. Right, my x squared, I can get that down to just x. So this is what this simplifies down to. Finally, 2x and square root of 15, right? I can combine them, multiply. I'm left with 30, the square root of 30x. Okay, the square root of 30x. And yes, I'm assured we could simplify down 30 into something even smaller, but sometimes it's just better to leave it as this value here. Okay. All right. All right. So then again, just to look at values here. All right. So when we looked at this guy, again, we combined them, we factored out, and then we had x squared by itself. So we could take this and write this as the x square root of 2 here. All right. And what it's saying is that definition we went on the other couple of pages is saying that this should be the absolute value of x, right? This should be the absolute value of x, meaning positive or negative x value, right? And the reason is why it says is the original two factors, okay, so the original two factors, square root of 2x and x, are only defined for x is greater than 0, okay, for x is greater than 0. So those values of x, have to be positive, is basically what it's saying here, all right? It has to be positive, because if I had these values, right, it's saying I can't take right now, I don't know how to take the square root of a negative number, right? I don't know how to take the square root of a negative number at this moment. So these expressions here, these factors, only work for values that are positive, right? Values that are positive. Okay, so even though I combine them here, okay, I have to remember that this was a positive x value and this is a positive x value. So when I take the square root of it, it's no longer positive or negative. That's not an option. This one is only positive. Okay, it's only positive. So we can leave out the absolute value bars. Okay, we can leave out the absolute value bars for this example here. Because again, if I had a -1 here, I don't know how to take the square root of a -1 at this point. So that makes it is undefined for us. All right. So then again, it works for rational expressions as well. So it works for rational expressions as well with the same property. So if I've got 4 over x and x over 2, I can combine them. Okay, I can multiply. When I multiply, I've got 4x over 2x. All right, I can then simplify. So x gets canceled out. 4 divided by 2 gives me 2. So I'm left with just the square root of 2 here. All right, when I combine this one, I've got 3x over 8 and x over 2. So when I multiply out, I'm left with 3x squared over 16. Okay, and now I'm going to split up and basically factor out any perfect squares that I might have. Right, so I've got square root of 3x squared over the square root of 16. All right, and I know that, and I don't know why they just didn't take it one more step further here. They took this top here, and they had this as the square root of 3 multiplied by the square root of x squared. Okay, so they took, and the square root of x squared gives us this x value. Square root of 3 can't be simplified down any further. But we know that our denominator here, the square root of 16, goes down to 4. Okay, it goes down to 4. All right, and again, you can see here they have this little thing, x has to be greater than 0 is what they're saying. Okay, so it can't be a negative number. It can't be a negative number. All right, and then it's saying, do you remember FOIL? Okay, yes, of course we remember FOIL. All right, but we can do this for radicals as well. We can do this for radicals as well. It's not going to be as nice all the time, but if it's necessary, we can do it, right? So if we look at our first terms, we have square and square, or sorry, square root and square root. If I multiply those two together, right, I can combine them, and it's like saying the square root of x squared. So that's how we get this x value here. All right, I have my outer, so that's my -3 square root of x. I have my inner, which is +2 square root of x. And then my last value there is -6. All right, then I can collect any like terms. All right, and hopefully you noticed that those are like terms because they have the same radical. They have the same radical. It's square root of x and square root of x. Okay, if it was square root of x and square root of x squared, those would not be able to be combined. But since they have the same radical and the same radicand, right, the same value underneath the radical symbol, they can be combined there. Okay, they can be combined there. All right, so again, then to confirm this, to multiply radicals with variables, follow the same rule as multiplying radicals without variables. Okay, without variables, you're going to follow the same rules that we've been doing. Okay, and we can look more at those as you go. All right, so again, you have to think about these. This is where it might get a little bit difficult here. All right, so if I was asking you to actually do this here, all right, you would have to put parentheses around both of these. Okay, so this is the quantity of x plus 5 multiplied by the quantity of x minus 2, right? So this would be one where you'd have to FOIL it out once you combine them. Okay, you wouldn't just be able to write the symbol and then go, okay, x plus 5, okay, 5 times x, right, whatever. These are quantities, so these would immediately have to be considered with parenthesis signs, all right? Have to be considered with parenthesis signs. All right. And then this here says which inequality represents the all values for x, which the product is defined, right? Again, it's where or what values are acceptable here in order to make this a positive value here, right? In order to make this a positive value. So if we look here, x plus 5 has to be greater than 0. Has to be greater than 0. So it has to be a number that is less than -5, for example. Right, in this one, I've got x minus 2. So x has to be a number that's greater than 2 here. All right, so our choice here, oh, okay, got it. All right, so apologies. I guess I misunderstood what the question was asking. All right, so this one here, this first guy has to be a value of x is greater than -5, right? So this first one here has to be greater than -5, all right? But if it's, let's say, -2, right? If it's -2, right? The factor applies to both of these. So if x was -2 here, it would be -2 here as well. All right, it would be -2 here as well. So this would be -2 minus 2, which would give me the square root of -4. And we don't know how to do that yet, right? So for this entire, I guess that's what it was saying, for this entire inequality, or for this entire expression, the inequality has to be greater than 2. Okay, it has to be greater than 2. Even though this first one here would be satisfied by B, all right, the second one requires a little bit more values. So we have to ignore, even though there are values, you know, like -4, -3, -2, that would make this okay, we have to consider both of those expressions there. All right, so that's what it's saying. It's saying think about the restrictions so that you need both are greater than or equal to 0. Okay, so again, both are greater than or equal to 0 there. All right, so then again, this one here, okay, you would combine them, but remember, this is an inequality, or sorry, not an inequality, I keep doing that. This is a quantity here, x plus 7. So when you combine these, this has got to be 3x multiplied by the quantity, right? So imagine if there's parentheses here, the quantity of x plus 7, the quantity of x plus 7. All right, so you've got to distribute 3x to x and 3x to 7. Okay. And then again, more practice problems for you, similar to what you're going to see on your quizzes for this unit here. Okay. You've got to combine like terms when possible, right, and get it to the most simple form here. Get it to the most simple form here. All right. So again, really going to come down to this kind of last one here, where you've got two fractions. You can combine them, you can separate them, right? Really playing with both of those principles that we now know. Okay. And then, as you can imagine here, the same concept is going to work for dividing radicals. All right, so if I've got a over b, right, the square root of a over the square root of b, they're going to just combine to the square root of a over b. All right, for any, again, positive values. Okay, so that's the key here. It's got to be positive values for both a and b. Okay, we can't have something that's going to make these 0. Or, sorry. We can't have something that's going to make the denominator 0, because that makes our expression undefined. And we also can't have something that's negative, because we don't know how to take the square root of negatives yet. All right, so looking at our example here, if I've got the square root of 12 over, the square root of 12 times x cubed divided by 3x. Okay, I can convert this to a fraction. So that's what it's going to look like here. And then I can combine them. All right, and then I can simplify by dividing by 3x if possible. So I'm going to get rid of an x value, and I'm going to take 12 divided by 3, which gives me this 4x squared value. 4x squared value. All right, and then since both of these are perfect squares, I can simplify them easy. The square root of 4 gives me 2, and the square root of x squared gives me x. Okay, and again, x has to be greater than 0 for this to work. Okay, x has to be greater than 0 for this to work. All right, because again, I can't have a 0 on the bottom. So if I look at this expression before I simplify it, what values of x would make this negative or undefined? And the answer is it has to be something greater than 0. Okay, any negative numbers would make these a negative. All right, and then for this one, if I have a 0 in the denominator, that makes my expression undefined. Okay, looking at example 2 here, I've got 6x divided by 2x squared. Okay, so if I look at converting that to a fraction, okay, I can combine them. I can cancel out an x from the top and the bottom, and I can divide 6 by 2. So I'm left with 3 over x. 3 over x. And the same thing, x just has to be greater than 0. Okay, we can't have something that's going to make this negative or make our denominator undefined here. All right. So if we're looking at this here, right, this goes back to that original question here. So where is x defined? Okay. So for this one here, okay, x just can't be negative. Okay, so anything greater than or equal to -3. Okay, anything greater than or equal to -3. Okay, because even if I had -3 here, this is going to be my numerator. -3 plus 3, that's going to give me 0. I can have a 0 in my numerator or a 0 on top of my fraction, right? That's acceptable, but I can't have a 0 in my denominator. So when we look here for possible values of x for our second one here, 1 minus x, okay? This can't be 0 because it's our denominator, and it can't be negative. All right, so this one has to be greater than 1. Okay, so if we were asking where this would work for x, the values are going to be greater than 1. Okay, the values have got to be greater than 1. Okay, so to satisfy both of those conditions, it's got to be between those two. So if x has got to be greater than -3, but it's got to be less than 1. Okay, it's got to be less than 1. These are the only values where x is going to be acceptable, because if I have a value greater than 1, right? So let's say x is 2, 1 minus 2, that's automatically negative, right? So we can't do that. So the only the only values that will allow this fraction to work, or this expression here to work, is going to be between our -3 value here of our first one and our +1 of our second factor here. All right, so again, I know that might be confusing, so let's take a second, let's redo that. All right, so again, looking our possible values of x, this one just can't be 0. Okay, it can't be, it can't be negative. So it has to be something that's going to make this expression greater than or equal to 0. So if I had x plus 3 equals 0, okay, x can be -3. All right, so it's got to be greater than or equal to -3. All right, it just can't be negative. This one here can't be negative and it can't be 0, because when we divide, we can't have a 0 in our denominator. So looking at this, 1 minus x, so our value for x needs to be less than 1. It needs to be less than 1. Because if I have a 2 here, again, 1 minus 2 gives me -1, right? I can't have a negative radical or radicand. All right, so I'm stuck. X has to be between -3 and +1. So we would write it as our inequality here. X is greater than or equal to -3 and less than 1. All right. So to divide two radicals, you should first write them as a fraction, right? We got to write them as a fraction. Then we can combine them if necessary and move on from there using our steps here. All right. So again, being really, really careful that these are quantities. So again, we would write this as our fraction here first, and then we would combine and solve from there. All right, so if we look at this one, it says which inequality represents all values of x for which the quotient is defined. Okay, all values. So for here, if we look at our second one, okay, this value just can't be 0. Okay, this value just can't be 0. All right, so this has to be greater than 0, because when I have it on bottom, I can't have a 0 denominator. All right, so it has to be at least greater than 0. All right, and then when I go over here, this value has to be greater than 8. Has to be greater than 8, because if I have a 7 here, right, 7 minus 8, that gives me -1. Okay, that gives me -1. So it has to be greater than or equal to 8. Okay, it has to be greater than or equal to 8. All right, and since this one is greater than or equal to 8 and this one was just greater than 0, okay, obviously we need to go with the more extreme conditions here to make sure we satisfy both of those. All right, so again, I'll leave these for you all to be able to go through and just really making sure that you're paying attention to writing out all the steps, drawing them in the proper fashion. I know especially with radicals, we can get a little bit lost. So make sure you're actually taking the time to write out all the steps like you see in the study guides, like you see in the answer keys. Okay, again, I know you can get a little bit confused here, so please make sure you're taking your time with these guys. All right. So again, a couple key reminders here. When you have something being multiplied by a radical, you want to make sure you write it out in front, because again, this kind of looks like, if it's a little squinty or you're unsure, it looks like the square root of 3x, where it's supposed to be x multiplied by the square root of 3. So please make sure you write them, in that form there. All right. And then again, being careful with our properties here. All right, so when we take the square root of a value squared, we're left with the absolute value of the original, right? So if I have x squared and I take the square root of it, I'm left with the absolute value of x. I'm left with the absolute value of x. For the opposite, right, if I have a square root of something, I can square it and again get back out my original expression. So if I have square root of x plus 1, I can square it and get out x plus 1 here. All right. Again, and then I can use the same principles of multiplication and division that I learned. I can combine those underneath the radical symbol. All right, I can combine them underneath the radical symbol. All right. And here, I think if you look at the answer key, they do a lot better job of showing the FOIL here than they did in the Apex actual lesson. All right, so again, just knowing that square root and square root, you multiply those together. Well, again, I'm going to be left with x squared, square root of x squared, which gives me my value of x there. All right, so knowing how to FOIL out an expression like that. All right, and then again, looking at the steps for dividing radicals and multiplying them together. Where the last step in both of those is, of course, finding the domain or finding the acceptable x values that are going to make non-negative square roots and no divisions by 0. Okay, no divisions by 0. So again, this is a good practice problem here to figure out, okay, well, where are those values going to be defined, right? What values are acceptable for those radicals there? All right. Looking quickly at the checkup. All right. Again, you're just doing the same thing. So you're going to first start off with writing the values where X is defined. Okay, so writing the inequality where X is defined. So what would make this not work? And again, the answer key does a nice job of showing for the division problems here. Okay, when we divide, you would actually bring that 2x down here. So again, the bottom, the denominator, can't be equal to 0 because we can't have a division by 0. So this is a good example of where it's not like this first one here where they both could be equal to 0 and that would be fine. Okay, we can't have the denominator equal to 0, so it's just greater than and not greater than or equal to. All right, so paying really, really close attention to that. Okay, and then simplifying down the expression based on the operations that are given, right? Are we dividing or are we multiplying? And based on those expressions given, simplifying down as far as you can. All right. So these are some really, really good practice problems. Even if you don't do them maybe for the first lesson, I really highly suggest that you do them for these variable problems. Okay, it's going to be really important moving forward here that you understand these concepts. All right, and again, apologies, but there's 2 quizzes for this one. Again, they're split apart into multiplying radicals for one quiz and then dividing radicals for the other. All right, so just like the last one where there's 2, okay, multiplying and dividing. All right, there's multiplying and dividing. All right, and then the last one we're going to introduce here is adding and subtracting radicals. Okay, adding and subtracting radicals. This is the last one we're going to have for today. All right, so if we understand how to multiply and divide radicals, okay, the next step we need to learn is how to add and subtract them. Okay, and we did have a little bit of introduction to that in that FOIL problem, but basically, again, in order to add and subtract them, they have to have the same degree and the same radicand. All right, they have to have the same degree and the same radicand. All right, so for example here, like terms. Okay, so if I zoom in here, like terms. Okay, so first off, they have to have the same degree and the same radicand. So personally, I look for do they have the same radicand, right? Square root of x, square root of x. Awesome. Okay, that can be combined, but I have to make sure they have the same degree. Well, this is a constant and this is a constant, so those can be combined here. All right, those can be combined. This next one here, radicand 7, awesome. Okay, so those can be combined according to this, but now we got to check. This is 2x to the first power. Okay, 2x to the first power. This one is 9x to the first power. So again, those are the same degrees. Those terms are the same degrees, so I can combine 2x with 9x. All right, same thing here. They have the same radicand. This is an x cubed and a 3x cubed. So this obviously is going to give me 4x cubed when I combine them together. All right, first off here, okay, this one has a radicand of square root of 4, and this one is square root of 3. Those aren't the same, so those can't get combined. All right, this one is square root of 2, and this one's square root of 2x. Again, this one is not the same. This one is a constant, and this one is a first degree term. All right. This one has the same radicand, okay, but this one is an x cubed term, and this one is a 7x squared term, okay? So I can't combine x cubed and 7x squared, all right? I can't combine those. Those aren't the same degrees, all right? So hopefully it's not too terribly new to you, okay? A lot of it, I hope, is just common sense, right? You have to make sure that they're the same, and if you wouldn't be able to add them normally, right, you're not going to add them with this radical symbol. All right. So if we look at a couple examples here, I've got a 3 square root of 6 plus square root of 3 plus square root of 6. All right. So when I collect my like terms, the only thing that's like is this square root of 6. Okay, the square root of 6. And you can imagine that there's a 1 out in front there, right? So when I add them together, it's going to give me a 4 square root of 6. All right, it's going to give me a 4 square root of 6. When I look at my next one, I've got a lot of different factors here. Okay, so first again, I'm going to look for like terms, which has the same radicands. Okay, they have the same radicands, and if they have the same degree out in front, we can combine them. So I've got an x and a 4x, right? So those can be combined. So I'm going to be left with a 5x square root of 3. All right. And again, when we're doing subtraction, it's going to be the same process, except for, again, just being careful with the negative sign. Okay, just being careful with the negative sign. So, for example, here, I've got my expression. I'm going to look for my like terms. So I'm going to have 2 like terms with the square root of 5. All right. So again, I'm just making sure that this one is like saying plus. So I have plus this value, and on this one is a negative, so I'm going to subtract that value. So 4 minus 6 is going to give me negative 2, right? So I'm going to have a negative 2 value there. Again, just being really careful with your negative signs here. Okay, when we collect our like terms for this one, okay, we're going to have a bunch of them. All right, so again, being really careful with that we have square root of 2, square root of 2, square root of 2, and square root of 2, but okay, you also have to match up the degrees. So these are terms with x to the first power, and these are terms with x to the second power, okay? And again, paying attention to which one is being subtracted, right? Just that last one, right? So this first one here is going to be a basic addition problem, and this second one here is just going to be a basic subtraction problem, all right? Hopefully not anything too terribly difficult. All right. So then here, there's some problems where they might not look obvious at first. Okay, they might not look obvious at first. All right. In what they suggest here is, in this case, you must simplify the terms as much as possible and then take another look here. All right, so before you just immediately look at a problem and say it's in its simplest form, okay, you might want to try to play around with it, simplify it further, see if you can add or subtract or whatever. And to simplify and find some like terms there. So if we look at example 1 here, they might not look obvious at first, but I can factor out a square root of 4 here. All right, so then once I factor this, I've got multiplied by 4 by 2. I can split those 2 up, right? I can split those 2 up. And I can simplify this down in 2 ways. 1, I can take the square root of 4, right? 2, I can combine those square roots of 2. So when I simplify, apologies. Even I tried to rush it a little bit. Okay, I didn't pay attention to the symbols there. All right, so this one's addition, right? So sorry, apologies. You can still square root this down to 2, but this is now going to be 2 square root of 2. All right, 2 square root of 2. So now when I add this, this is like a 1 out in front. I've got 1 square root of 2 plus 2 square root of 2. That's going to give me my 3 square root of 2. All right, so I can simplify this down further. All right, again, I'm a perfect example of why you need to make sure you go through this slowly and carefully, writing out all of your steps. Okay. For the next one here, square root of 27 and 3. All right, might not look obvious until I factor out a square root. Okay, I've got 3 times 7, that would give me, 9 times 3. Wow, 3 times 7. Wow. 9 times 3 there. Okay, 9 times 3 gives me 27. All right, so if I look at this, I can then split these guys up. I can take the square root of 9 multiplied by my square root of 3. So I'm going to be left with 3 square root of 3. All right, and then I had my original square root of 3. So this is like saying 3 plus 1 here, and I'm left with 4 square root of 3. All right, and my final example here is I've got square root of 20 and the square root of 45. So I'm going to look and see if I can factor out a square out of both of these, right? Out of both of these, they can get simplified down further. So I'm left with 4 times 5 gives me 20, and 9 times 5 gives me 45. So what you can see here is I have perfect squares in both of these. I'm going to split these guys up. So this is going to give me, this first factor is going to give me 2 square root of 5. This is going to give me 3 square root of 5. All right, and once I do that, I can add 2 plus 3, which gives me 5. So I'm left with 5 square root of 5 here. And I'm left with 5 square root of 5 here. All right. So then finally here, to just confirm what we know, you can add or subtract two radical expressions only if they have the same degree and the same radicand, right? They have to have the same degree out in front and the same radicand underneath that radical symbol. All right. So again, combining like terms, being careful with, you've got to make sure that you have the same degree, the same radicand, and you have to pay attention to symbols, especially when we're doing subtraction and addition here. All right. So again, the first term here and the last term, those are the ones that are going to get added together, and then you have subtracting that middle term there. All right. So I'll let you work on those problems. Same thing. All right. So again, this is a perfect example of it. Doesn't look like they can combine right off the bat, but if I can simplify down the square root of 12 here further, okay, this is going to give me the square root of 4 times 3, right? And then this is going to simplify down to 2 square root of 3. So I'm going to have 2 square root of 3 plus 3 square root of 3, and that's going to give me my 5 square root of 3. All right. Again, this one here, can either of these get simplified down further? And the answer is yes. You're going to notice both of them can get simplified down further. Okay, they can both get simplified down further. So then they can get added together there. All right, so again, just more practice problems. Again, especially those with subtraction signs, just paying attention to the negative signs there. All right. So then final couple minutes here looking at our study here. All right, understanding why things can't combine is going to be really, really important. All right, and again, just taking your time to actually notice the minute differences. All right, making sure that you're noticing those differences here. They don't always have to add together. All right, and then write a matching term. Okay, so these could be a lot of different answers, but again, all you have to make sure is that the radicand is the same, the exact same, and then the value out in front just has to have the same degree. So this could have been a 6, 16, 62, whatever. Okay, this one could have been 5x. It could have been negative x, negative 3x, whatever, as long as it just had x to the first power here. All right. And then similar processes here for adding and subtracting expressions. All right, we are going to and really there should be a step 0 here that we just found out. If it's not already done, make sure you simplify, right? Simplify the terms you're dealing with. Okay, and then once they're simplified, you're going to collect those like terms, add or subtract them depending on whatever their operations were, and then simplify down as necessary. Okay. Oh, perfect. Sometimes you need to simplify radicals. Okay, so perfect. My step 0. All right. All right. So then finally here, looking at our checkup. Okay, looking at our checkup. You're gonna have obviously more practice problems that I suggest you go through. Okay, and they're gonna ask you to just simplify the expression. In 2 different cases. All right, so if we look at this first one here, this is just dealing strictly with normal values at first. Okay, so dealing with values with no variables. We get a little bit into variables here. And then in 8 through 10, we really step it up with using those variable values of x. Okay, so just again, being very, very careful that it's the same exact processes, right? You just treat the variables like numbers, or treat the numbers like variables, however you think about it. All right. And again, being careful with that, even if we look at this first one here, okay, square root of 24, square root of 54, and square root of 150. It doesn't look like they can all get added together. But remember, step 0, you have to simplify these expressions down, see what you can factor out. So if we actually take a look at these are all factors of 6. They're all factors of 6. 4 times 6, 9 times 6, 25 times 6. So when we simplify them all down, they're going to end up with this radical of 6, square root of 6. All right, so then they can get added together pretty simply here. All right, again, paying attention to negative symbols. All right, so hopefully not too terribly difficult. Okay, hopefully not too terribly difficult. And thankfully for this one, there's only one quiz here. All right, there's only one quiz. So again, if I can remind you of what you need to do today, all right, or what you should do today to keep up with the pace that we've set. All right, we went over lesson 2.1, which has 2 quizzes that are both mandatory. We went over lesson 2.2, which has 2 quizzes that are both mandatory. All right, and then we have lesson 2.3, which is 1 quiz. Okay, lesson 2.3, which is 1 quiz. All right, so sorry, today you have 5 quizzes, but thankfully tomorrow's Friday. All right, thankfully tomorrow is Friday, and we don't have class, so you have some time to work on these. All right, so that's what we're gonna cover, or that's what we covered today, and that's what you should cover tonight for your, hour and a half or however long of work that you have to do each day. All right. Last thing here is apologies. So lastly here, the last thing is that this weekend I will post 1 video. So unfortunately or fortunately, whatever you would want to call it, okay, when we were looking, right, if we break our work week up into 5 days, right, that's how we got to about 3 lessons a day, assuming that we were working at least 1 day on the weekend, right? So a Friday, Saturday, Sunday, right? So I will post tomorrow. I'll go with tomorrow morning. I'll post it for you guys so that you can have it and work on it all weekend. I'll post just 1 video lecture, okay? It'll be probably around an hour and a half, maybe 2 hours at most. But I'll post 1 video lecture tomorrow morning that covers the units that you should look at this weekend, okay? So you will have a little bit of homework this weekend if you want to keep up with this pace, and then we will reconvene on Monday. All right, so just a reminder, there is no Zoom meetings tomorrow, okay? But I will post a lecture video that you should look at sometime this weekend. All right, and for everybody, I'll just post it as a YouTube. It's not going to be an Edpuzzle, so watch it at your own leisure, okay? And then we will reconvene on Monday, okay? We'll reconvene on Monday.